And we have here the transform fault boundaries. At the transform fault boundaries, plates are grinding past each other without destroying the lithosphere. So they are basically transform faults. They are just sliding parts past each other as a result of the uh, overall movement in relation between two plates. At the time of the formation, they were roughly parallel at the direction of the in between the two plates, and they aid the movement of your oceanic crustal material also. So in your convergent boundaries, and also your in our example here in our divergent boundaries, your your divergence is not exactly equal with the speed or the pace of divergence is not exactly equal towards each other. For example here, this upper portion of your divergent plate is diverging faster towards the left than to the right. Then at the bottom portion of our example, it is actually diverging faster towards the right than to the left. And in turn, it makes this transform fault boundary, which basically they are still the boundary of two plates that are moving each other in relation. So that is one reason of your transform fault boundaries. That is how it is formed. One is the differential motion between your convergent or your divergent boundaries, uh, and another one is your plate is just moving in parallel towards each other. Like for example, your San Andreas plate, which is a right lateral plate where the Pacific plate is actually moving uh, northward northwards in relation to your North American plates, which is relatively either slower or moving southwards. Okay, so that is how your San Andreas plate was formed. Okay, so next is the evidence for your plate tectonics. So, but one of the evidence is paleomagnetism, which is the natural remnant of your magnetism in rock bodies. This is the permanent magnetization or acquired by the rock that can be used as the location. So, this was one of the evidence that was used for your seafloor spreading, wherein your normal polarity is basically the same as our polarity today, where our magnetic north is the north that we are using, and the south is it's the south. And then if it is the reverse polarity, our compass would be in reverse, wherein the compass would be instead of pointing north, our magnetic north, it will be pointing south because our magnetic field was uh, changed its polarity or it reversed its orientation. So uh, that's the that's the difference between your normal polarity and your reverse polarity. So it one of the good examples was based in your lava flows, wherein your uh, magnetic iron minerals were oriented at the time of were oriented based on the polarity at the time it was crystallized or formed. So, for example, recent eruptions had the normal magnetic uh, was using the normal polarity, and then still until zero point 0.4 years ago, zero point 0.4 million years ago, is still a normal polarity, and eventually uh, at zero point 0.8 million years ago, there was a reversal of the polarity, and then again back to the normal polarity 1.2 million years ago. So, our there are cases that the polarities are suddenly changes. Okay, so our magnetic north goes to south, and the south goes to north. That's it. So, it is reflected in our towards the orientation of our magnetic iron minerals. in our uh, uh, magmatic or igneous rocks. So, as an evidence for plate tectonics, the discovery of the strips of alternating polarity which lie in the mirror images across the oceanic ridges is among the strongest evidence of the seafloor spreading. And this was used as the evidence for the seafloor spreading hypothesis, uh, seafloor spreading hypothesis by Harry Hess and Robert Dietz for the seafloor spreading, wherein they found out that there were alternating or mirror images of different polarities of your magnetic minerals in uh, in your seafloor. Okay, so that's it. So for example, same concept as the earlier volcano. So for example, if we have here a normal polarity and then there is a period of reversal polarity, and then there was another stripe of a normal polarity. Basically, as said earlier, the magnetic minerals are oriented towards the polarity during the time of crystallization. And also we have earthquake patterns, which found a close link between deep focus earthquakes and ocean trenches. The absence of deep focus earthquakes along the oceanic ridge system was shown to be consistent with the new theory. And then based also on ocean drilling, they found out that the seafloor hypothesis, spreading hypothesis was predicted, wherein they found out that the fresh and the youngest oceanic crust were found at the ridge, and the oldest oceanic crust is at the continental margins. And they also they using this theory, they also found out that the subduction is also true, wherein the oldest rocks that can be found at the convergent boundaries were said to be 150 million years ago. It's still in between the time of the dinosaurs, wherein the age of the Earth was so in fact was dated at 4.6 billion years ago. So how can that be? Where what happened to the next 4 plus 4.5 billion years of data gone. So it was eventually concluded that it was abducted towards the mantle. And also, we have your hotspots. So a hotspot is basically a mantle plume or the hot part of the mantle which rises towards the crust and eventually creates a volcano, a smooth flowing volcano wherein the concentration of heat in the mantle is capable of producing magma which rises towards the Earth's surface. And for example, the Pacific plate moves over the hotspot. So the hotspot uh, is actually stationary, wherein your overriding plate is moving. So if you're moving your hotspot on an overriding plate, it's making a train or a trail of volcanoes behind it. So this produced our good present day example would be the Hawaiian and the Emperor Island seamounts. The yeah, the Hawaiian Islands and the Emperor Island seamounts. Um, so the hotspot evidence also supports that the plates are moving over the Earth's surface. Okay, so yeah, like said earlier, this is uh, the Pacific Plate, the mantle plume, and the hotspot. So present day, it's currently in the Hawaiian Islands, and based on the direction of the plate movement, we have formed there. The movement of the Pacific Plate was then concluded that it is moving at this direction. So we have the Hawaii, Oahu, Molokai, Maui, then Hawaii. Then, so the next component, since we have the carried product, we have the we have the other carried product which is pushing basically each other, the next we will have what is making this stick, what our conveyor belt plate tectonics is, what makes this move. So basically, scientists generally agree that the convection occurring in the mantle is the basic driving force for the plate motion movement, and this was coined by Arthur Holmes. Okay, so the convection flow is the movement of the matter resulting from the changes in temperature, wherein the hotter mantle material is going upwards and the cooler mantle material is going downwards. So basically, uh, it is continuously flowing up and down and carrying, and that motion, it is also carrying your rigid plates up top. Okay, and then one of the evidences was the slab pull and ridge push. Okay, so the slab pull is the mechanism that contributes to plate motion in which the cool, dense oceanic material is being pulled by the mantle. Okay, is being pulled by the mantle towards the mantle, of course, and then the ridge push, since the upwelling of hot mantle material when it solidifies up in towards the surface, it is actually pushing the oceanic crust sidewards. Okay, so and also by using gravity. So both of those components are actually at the both ends uh, of your oceanic crust being subducted, having the slab pull, and being spreading, having the ridge push. Then you have another uh, causes of your or maybe a product of your mantle convection, that they also have the mantle plumes, which are masses of hotter than the normal mantle material. So these are related to your hotspots. So the unequal distribution of the heat within the earth causes the thermal convection in the mantle that ultimately drives the plate motion, where basically at some parts of the mantle, after subducting, or there will also be or parts that hot mantle material is rising uh, that are not really related to your divergence. So this causes your mantle plumes. And so this is how the two theories work. So we have the uh, multiple what you call this convection theory and the one mantle convection hypothesis. And that is all for plate tectonics. Thank you, and thank you for listening.